Hello everyone, my name is Shauradip. I'm currently working as a software engineer at SLB, and previously I was a master's student in computer engineering at Purdue University. Today I will be talking about our paper, Time Constraint Recommendations, Reinforcement Learning Strategies for E-Commerce, which is co-authored by Shayak Chakraborty, who is a computer science PhD student at Northwestern University. Our paper is related to Slate recommendations, where users are recommended a list of K items together, which is called a slate. The items are recommended based on item relevance and several other factors. The recommended system firstly generates item relevance scores for all available items and then inserts the relevant item at slot K after inserting K-1 items. These are some of the maths behind this process, showing how the items are selected by the item sampler for the kth slot. Here, beta k is the probability of choosing the kth item, skipping the K-1 items based on the relevance of the kth item, and the probability of generating the slate is their summation. Now in e-commerce, there are additional constraints to this slate recommendation problem. Usually in e-commerce, users are generally presented with K items via scroll or search in a mobile shopping interface. The user checks out each item sequentially, which is a cost Ci for the ith item, and the user then interacts with the interface via clicks. Once the user's time budget U is exhausted, the user abandons the interface. Thus here, the user's time budget is a critical resource which must be taken into account by the system while recommending items. The idea is to show items with higher utility per second in order to improve satisfaction, and this gives the optimization problem to maximize the probability of generating the slate such that the cost of item evaluation does not exceed the user's time budget. There have been a lot of prior works done in this area. Initial works formalized slate recommendation NDB framework using a combinatorial approach, where the recommendation agent learns values of individual items independently and selects the top K items. Later, SlateQ introduced a new method to decompose the value of slate into item-wise components, making it practical to do value-based Q-learning. Other works introduced several new training frameworks for list-wise and page-wise recommendations using environment simulation via ranking and sampling. However, all these works focused mainly on item relevance derived from click-through rate without considering evaluation time constraints. As a result, they placed items with high evaluation cost earlier in the slate, which increases abandonment and reduces user engagement. In this paper, we introduce a new approach to recommend slates, assuming finite user attention or time budget. We model the problem as a Markov decision process where we optimize the slate configuration by balancing item relevance as well as evaluation time cost. These are the parameters of the MDP framework. The state consists of the user's remaining budget and the list of K-1 items which are already inserted into the slate. The action is to select the relevant item for the kth slot. Rewards are sampled from the Bernoulli distribution based on the item relevance and clicks if the evaluation cost fits within the time budget. And at each step, the time budget is reduced by the cost of the item evaluated. To get the slate generation probability and design rewards on clicks, we need to compute item relevance. For this reason, we employ a personalized re-ranking model to generate item relevance scores denoted by sigma I for the ith item. The model learns a personalized vector representation of the items and captures item and user item relations via transformer encoder layers on top of the item and user embeddings created from raw features. From the item relevance scores, we derive the log relevance denoted by log beta I for each item used for reward computation. For the training of the PRM model, we use the Alibaba's re-ranking dataset consisting of 150 users, 150K items, and 30 items per slate. Subsequently, we use reinforcement learning algorithms to recommend the best slate. For learning the optimal policy in the process, we need some additional data for simulating the environment. For example, the item evaluation costs were sampled from a uniform distribution with lower limit 0 and upper limit 100. The initial user budget was also sampled from a normal distribution for each experiment with different mean budget. A user choice model based on multinomial logits over item relevances was used to simulate the user clicks and generate rewards. Once all the parameters of the environment are obtained, we can now generate trajectories to optimize the value function using SARSA and Q-Learning algorithms. An XGBoost model was used as a function approximator along with an epsilon greedy policy to generate the next item in the slate. This diagram shows the overall RL simulation technique where, starting from a random slate of k items, we iteratively generate the next reward and states and learn the optimal value function to get the best slate configuration. Here we use two metrics to evaluate the performance of the different RL methods used. The metrics are called play rate and effective slate size. Play rate measures the average number of successful engagements or clicks for all users. It gives an idea of how well the items are placed in the slate such that there are more clicks by any user. And the second metric is called effective slate size, which refers to the number of items that the user can actually see before exhausting their budget, averaged over all users. For example, if on an average, if an user can check out only 10 out of the 30 items on the slate, then the effective slate size is 10. Here are some of the results we observed on running the SARSA and the Q-Learning algorithms to optimize the slate. We ran experiments for different initial user budgets, ranging from 100 to 500, and also for different discount factors, ranging from 0 to 1 with several random seeds. It was observed that for moderate budgets, the SARSA, which is an on-policy algorithm with positive discount factors, performed better than myopic contextual bandits where the discount factor is 0. Also for larger user budgets, SARSA provided better effective slate sizes than Q-Learning, although play rate, which I will show in the next slide, was much lower than Q-Learning. This generally implies that the users were able to explore more items within the time budget, which means that SARSA was able to reduce the probability of abandonment. We ran similar experiments for Q-Learning as well, which is an off-policy algorithm. It was observed that with a positive discount factor, Q-Learning also performed better for all budgets than myopic contextual bandits where the discount factor is 0. Moreover, Q-Learning provided better play rates than SARSA, although the effective slate sizes were almost similar to SARSA. As you can see, for all the budgets, the play rate in case of Q-Learning was much higher than SARSA, which implies that the user successfully clicked on more items in the slate, although the time budget was exhausted quickly. So the key takeaways from these experiments are that both the value-based reinforcement learning algorithms, SARSA and Q-Learning, perform better than contextual bandits if the user time budget constraints are taken into consideration while building the slate. This new constraint definitely affects stability of learning, the best policy, although Q-Learning proved to be quite stable in this case, maintaining consistent reward advantages as seen by the high play rate achieved for all user budgets. Also for tight budget constraints, Q-Learning can be quite effective due to its off-policy nature, as it is robust against exploration even when the initial user budget are small. These are some more observations that are noteworthy. SARSA performed a bit better for moderate budgets than Q-Learning, as moderate budgets provide longer episodes, which helped in mitigating the noise due to exploration. However, if the budgets are even higher, it led to more exploration, which in turn resulted in poor value estimation in SARSA, thus decreasing the performance. Also, Q-Learning had better results with higher discount factors due to emphasis on long-term value gains, leading to better policies. Here are two graphs showing how the difference in play rate and effective slate size percentages between two extreme discount factors varies with user time budget. As can be seen, for lower user budgets, Q-Learning performs better for larger discount factors, whereas SARSA does the opposite. However, with the increase in the budget, the effect of discount factor diminishes, and the difference in the play rate and effective slate size becomes almost close to zero in both cases. Coming to the future plans, here is a list of future research directions that we plan to explore. Instead of sampling the item evaluation costs independently, we can assume the cost to be a learnable parameter, depending on the position and the feature of the items. The best would be to use some real-world dataset from which we can infer some notion of the evaluation cost of these items. Next, we also plan to explore policy gradient methods, which have evidently shown better results than value-based methods in other domains. Also, we intend to allow different action types for users to interact with the slate, having unique rewards for each such action, for example, clicks, add to cart, purchase, etc. And in general, user budgets are time varying and should be modeled as such using partial observable MDP approaches, which can better capture variations in real-world slate recommendation scenarios for e-commerce use cases. These are some of the references that helped us in this research. Thank you very much for listening to our presentation. You can check out our code and paper by scanning these QR codes. If you have any questions, please let me know. Thank you.